All right, so next we're going to look at negation of quantified proposition. All right, so it's like you can think of the universal existential quantifier as generalized conjunction and disjunction statement. So for all, it's like a conjunction. So like all the propositions have to be true. And for the existential, at least one of the proposition has to be true, right? So when you negate an existential or a universal quantifier, this is like De Morgan's law, right? So this is more like a generalized De Morgan's law. Let's see. And remember, De Morgan's law gives you the rules for negating composite propositions with and or. Okay, so we can look at the first statement here. Should be an extra parentheses. So if I'm negating the universal quantifier for all n, then P of n is true. The negation becomes there exists an n in the universe such that P is not true for that n. Right? And if I'm negating the existential quantifier, there exists n in the universe for which P of n is true, then the negation of that is that P of n is going to be not true, P of n is going to be false for all values of n in that universe. So let's look at a couple of examples. So example 7, we're going to negate these statements. So let's look at there is an honest politician. Okay, let's write it in symbolic form first. So there is an honest politician. That would be an existential statement. So there exists an x h of x. Okay, so let's say my universe is all politicians all right, then there exists an x such that h of x is true. Basically, h of x is the proposition that a politician is honest. Okay, so if we negate this, right, so if we have the negation of the existential quantifier, then this, you can see here, is going to turn into all politicians and then negate the h. Okay, so for all politicians in my universe, they're not honest. Okay, so this means, if we write it in English, all politicians are dishonest. All right. Okay, let's look at this statement. So all Americans eat cheeseburgers. Okay, so let's say that X is, my universe is all Americans. Okay, and you can see it's important to define your universe at the beginning. We'll see this later on too. So all Americans is my universe. So all American is cheeseburgers. Let's have C of X is people who eat cheeseburgers. So eat cheeseburgers. And so we translate this as all X CX. So all X's in my universe, all Americans, this is true. They eat cheeseburgers. All right, now let's negate this. So if we're going to negate this statement, okay, with the negation for the universal, this becomes there exists an X, so not C of X. Right, so what does this say in English? It says that there exists at least one American that doesn't eat cheeseburgers. That will be me, because I'm vegetarian. And other people. All right, so there exists at least one American who does not eat cheeseburgers. There you go. All right, let's look at example 8. Okay, so we're going to look at the negation of these mathematical statements. So let's write this down. This first statement, this is for all x, x squared is bigger than x. Okay, and the universe is not mentioned. But we can take it as, I know that it's true for integers, not true for all real numbers. So you can take the universe to be integers if we wish. But if we negate this, then this is going to turn into there exists an X such that this is not true. So there exists an X such that this inequality is not true. And we can rewrite this as there exists an X such that X squared is less than or equal to X, right? If we negate that inequality, X squared is greater than X, then that becomes X squared is less than or equal to X. All right, let's look at the second one. Let's say we have there exists an X, so X squared equals to 2. Okay, if we negate this whole statement, then this becomes for all X in our universe, this statement is negated, this statement is not true, and we can say that for all X in our universe, X squared is not equal to 2. I mean, sort of, again, we're not really looking at whether these statements are true or false. We're just learning how to negate. All right. All right, so as I mentioned, this is called the De Morgan's law for quantifiers, and this is the summary of it. And so if you're negating a universal statement, then that changes to an existential statement of the negation of the proposition. So for every n, Pn is false, turns to there exists an n for which all of Pn is false. All right, and if you negate the existential statement, then you get the universal statement of the negation of your statement. All right, let's now look at some translations. I'm going to translate some sentences using the universal quantifiers. All right, so we'll see that the universe that we take is very important in the translation, and it will change things depending on what the universe is. All right, so let's look at this statement right here. So every student in this class has studied calculus. And we're going to take the universe to be all students in this class. All right, so let's kind of take our variable, the students, and in this class, and our proposition that we're interested in will be defined as X has taken calculus. All right, so the way we translate every student in this class has studied calculus, that will be the universal quantifier. So for every X in our universe, for every student in this class, C of X is true. X has taken calculus or has studied calculus is true. So that will be translation based on the universe of just our class. But let's see how this changes if we take the universe to be all people, so all people in the world. So X is all people. All right. Well, again, let's have X, C of X be X has studied calculus. Okay. But because we're taking the universe to be all people, we need another statement that specifies that that person is in this class. So we're going to say d of X is that X is a student in this class, in discrete math. That's why I chose D, in this class. Okay. So every student in this class has studied calculus. Really, this statement, you can think of about it this way. So if the student is in this class, then that student has studied calculus. So if the student is in this class, then they have studied calculus. Right? And this worked for all, I don't know what that word is. Let's try again. For all people. Okay, so everybody, for all people, if the student, if the person is a student, so if the person is a student in this class, then they have studied calculus. So let's see how we write that. So for all X, for all people in the universe, on the world, if the person is a student in this class, then they have studied calculus. All right, so that's what the translation looks now, right? So changing the universe will change your translation to this. Okay, so notice that sometimes a common mistake is to use and instead of the if-then statement. A common mistake. Or this one is saying for all X, dx and cx. All right, so this is incorrect. Because this actually says for all people in the world, these people are both in this class and have taken calculus. Okay, and then our class would become like way too big, which we don't have enough seats. Although, because we're doing it remotely now, then we could actually fit all the people in the world to take this class. But anyway, there we go. So this is incorrect to use the and. You want to use the if-then statement to translate this. All right. Okay, so now let's do another translation. You might want to pause for a few minutes and try this out on your own and then come back. All right, so let's look at, we have two statements here. So let's look at the first statement. some student in this class has visited Mexico. Some student in this class has visited Mexico. So we're going to take the universe to be students in the class to start with, and then we're going to change it so the universe is all people. All right, so here's with this universe right here. We're going to say X is a student in this class. And let's call M of X the fact that X has visited Mexico. Right. So we're going to say some students, that means there exists a student X such that that student has visited Mexico. Okay, so that is the translation for that. All right, now let's change the universe so the universe is all people. So when that happens, X is going to be a person in the world. So just a person in general. And we're going to say D of X is that X is in this class. And M of X is that X has visited Mexico. Okay, so the way we say that is there exists a person X, so that person is in this discrete math class, and that person has visited Mexico. Okay, so because we're talking, the existential quantifier just refers to one person. So this will have the end, because that one person is both in our discrete math class and has visited Mexico, so that makes sense as a translation. All right, let's look at the green. Okay, let's look at this second statement. Every student in this class has visited either Canada or Mexico. And let's look at the universe being just our class. So X is a student in this class. All right. And let's say C has visited Canada. And M of X is that X has visited Mexico. Right, so every student in this class, has visited Canada or has visited Mexico. Right, so either Canada or Mexico, like this. All right, now we're going to change it to make the universe all people in the world. Right, so universe is all people, then X is a person. All right, let's use, again, dx is, X is in this class. All right, and Cx and Mx just as above. So Cx is that X has visited Canada, Mx that X has visited Mexico, so we're going to use the same definitions here. All right, so we're looking at every person, every student in this class has visited either Canada or Mexico. So every, that's the wrong one, every X, so every person in the world Now we have to specify that if that person is a student in this class, then they have either visited Canada or they have visited Mexico. There we go. So that's the translation of that statement. All right, so we can kind of sort of got a taste of how to translate sentences that involve existential and universal quantifiers. Okay.